Most traditional relational databases exist in a state of permanent amnesia. They are designed to manage the present tense and only the present tense. When an application executes a standard SQL update command, it does not add new information to the ledger. It replaces the existing record. At the mechanical level, the database engine locates the specific sector on the storage disk and physically overwrites the existing data cell with the new value. This architecture is inherently destructive. The previous state of the record is erased from the storage medium to make room for the update. This creates a structural blind spot known as historical amnesia. The database can retrieve a customer's current address instantly, but it cannot tell you where they lived last Tuesday. For a standard retail website, this is a minor limitation, but in banking, in medical tracking, and in insurance, the loss of past records is a catastrophic failure of the audit trail. Critical enterprise systems cannot rely on databases that only understand now. They require an architecture engineered to preserve the sequence of historical truth. The mechanical solution to this problem is the temporal database. Instead of capturing a series of isolated snapshots every time a record changes, a temporal database natively tracks continuous historical timelines. Tracking history mechanically requires abandoning the single date stamp. A single point in time can mark an event, but it cannot represent a duration. Instead, temporal databases construct chronological intervals. An interval is a data structure requiring both a definitive start point and a definitive end point. When you evaluate overlapping intervals, like a patient taking 3 different medications over varying weeks, you exceed the constraints of a standard one-dimensional table. Mapping these overlapping life cycles requires treating time as a multidimensional property of the data itself. By transforming time from a destructive event into a structural dimension, the database ensures that no previous state of the data is ever lost. Building this model requires tracking 2 distinct dimensions of time. The first is valid time. Valid time is the exact time frame when a fact is objectively true in the real world. When an event begins, such as a patient being diagnosed with a condition, the database records the opening of a valid time interval for that specific fact. When that real-world state changes, the system does not overwrite the record. It closes the existing interval with an end date and opens a new one to represent the updated state. However, relying exclusively on valid time exposes a vulnerability during a corporate audit. Consider a scenario where a contract is signed on Monday, but the paperwork isn't processed and entered into the database until Thursday. The valid time started on Monday, but the system didn't actually know it for 3 days. Tracking real-world truth is insufficient if the system cannot prove exactly when it learned that truth. This introduces the second required dimension, transaction time. Transaction time is the immutable system timestamp applied when the record is physically committed to the database disk. It explicitly captures the chronological gap between reality and the system's awareness of that reality. Combining axes creates the bitemporal model. Records map as rectangles bound by real-world duration on the x-axis and system entry on the y-axis. During retroactive updates, the original rectangle remains locked. The system plots corrected data as a new rectangle at a later transaction time. This allows an administrator to query against the y-axis to see exactly what the system believed was true at any specific moment in the past. This dual-axis plotting aligns the corporate ledger with the timeline of real-world events, ensuring every correction is as transparent as the original data. The shift from discrete points to overlapping intervals forces a corresponding change in how we retrieve that data. Standard SQL operators like equals or greater than are built for static values. They fail when applied to overlapping durations. To evaluate multidimensional records, the system employs temporal logic. Instead of exact matches, the engine evaluates chronological intersections between distinct durations. The system uses specialized operators, checking if one duration occurred strictly before or after another, or if one interval completely contains a shorter one. Additional operators like overlaps and during allow the database to isolate complex interactions, such as identifying every patient prescribed a medication during the exact month a recall was active. Evaluating these multi-dimensional histories requires replacing standard discrete math with this interval logic. Running interval logic across millions of rows introduces a mechanical bottleneck, disk indexing.
Traditional databases maintain search speeds using B-tree indexes, but standard B-trees are optimized for one-dimensional, discrete data, like ascending ID numbers. When you force a one-dimensional index to sort unpredictable, overlapping time intervals, the entire mathematical structure breaks down. The database loses its shortcut. To find a historical record, the engine is forced to execute a full table scan, reading every single interval on the storage disk. The architectural solution is the extended B+ tree, often implemented as a time-split B tree. Instead of sorting by sequential numbers, these indexes partition bitemporal data directly along time dimensions, dividing internal nodes based on chronological boundaries. Time-split B-trees maintain efficient search speeds even as the database grows to house decades of historical updates. The complete temporal architecture combines bitemporal intervals for storage with time-split B-trees for retrieval. This brings temporal architecture into the same mathematical territory as spatial databases. Both treat their primary subject, a map location or a timeline duration, as a geometric object. Both abandon standard table sorting to group complex geometries, solving for spatial width and chronological duration. This architecture provides the backbone for immutable banking ledgers, persistent insurance policies, and medical tracking networks. In these environments, an update is never an overwrite. The past is never compromised to accommodate the present. Through advanced database engineering, time is no longer a destructive event, but a fully queryable dimension of truth.